Hi everyone, my name is Aly El Gamal. I am a senior applied scientist in the industry, and before that I was a professor at Purdue. And today's talk is about analogies or commonalities between two very important disciplines that resulted in a lot of progress in engineering solutions in the 20th and 21st centuries. And these two disciplines are information theory and deep learning. And they share a common application, which is wireless communication. That's why that will be part of the focus of the talk, is to discuss the wireless communication applications. But the key objective of the talk is to highlight the similarities and try to learn from the lessons or key insights behind these similarities in order to make progress moving forward. And basically, the claim of the talk is that there are foundational analogies, which is basically in the philosophy behind each of these disciplines, there are similarities in their foundations. So I'll start with a historical perspective with information theory that was founded in 1948 via a paper by Claude Shannon called A Mathematical Theory of Communication. And then we'll discuss examples of through the wireless interference networks to further highlight the philosophy behind information theory into advancing both engineering solutions as well as scientific research. And then we'll go through an introduction of deep learning and then the application of deep learning to wireless. And we'll specifically focus on the analogy to the same principles related to the foundation of information theory. And then we'll end up with proposals for the path ahead into new applications for deep learning, and specifically through the example of the application of deep learning to wireless communications. So since wireless communication is a common example, core example between the two disciplines, let's just discuss an introduction. So the problem is very simple. You have a message or a word, let's denote it by W, and you want to deliver it to the other side. And so the engineering problem is to design an encoder and decoder so that you can communicate that message in the most efficient way and with as much information as possible through a medium that we will call a channel, right? Let's denote Y as the receiver, X as the transmitter. So the channel is defined by the conditional probability of Y given X. Now, that problem was a very important problem in the early 20th century for developing wireless telephones, right? And there were so many solutions that were ad hoc, and partial progress has been made before 1948, mainly through Nyquist. If you know, like the signal processing, Nyquist rate, and so on, that was in the 1920s. So the problem is that this problem is very rich in terms of the parameters that we can control for encoding and decoding, whether it's the transmit power, the modulation coding scheme, or even for the channel itself, we have the option to decide among a range, which is usually a wide range of center frequencies as well as bandwidth, right? So we get actually to choose some properties of the medium that we communicate over. And the objective has been always to obtain a satisfactory performance for the application. But the problem is there was no rigorous guidelines. So before 1948, even people didn't know how much is the cost of digitizing things, right? So we didn't know whether the capacity, is it sufficient to characterize it by a digital characterization, or maybe going digital in itself can cost us, because the capacity is inherently analog, right? So there was a lot of waste of engineering resources before the 1948 information theory paper came out, the Mathematical Theory of Communication. And that paper, the main focus was wireless communications, but interestingly, it went one step beyond the application into defining what information means as a measure of uncertainty, and defining mutual information as a difference of entropy, and defining what the channel capacity is, and starting to characterize, for simple examples, some of them are common in nature, like at least the approximation is not far from reality, like the Gaussian channel. And some of them are abstract, but agreed upon that they are important, that like the discrete memoryless channel. So in summary, this theory helped us to do a point-to-point characterization of channel capacity. By point-to-point, I mean between a transmitter and the receiver. There is no interference, there is no networking or anything like that. Now, a very nice thing about information theory is the goal for the wireless communication application was to characterize the channel capacity, was to know the potential of the medium that we are communicating over, right? So typically there are two sides to the proof of a channel capacity. One is a lower bound, meaning that the capacity is greater than or equal something. And this is usually called an achievability proof. Why is it called like that? Because it's typically the case that we don't have a concrete answer for the exact engineering design to reach this channel capacity, but we have a proof of existence, meaning that we can find a large family of codes and prove that within this large family of codes, there exists a code that achieves this capacity. And in order to do that, we rely on a mathematical technique called probabilistic existence that actually existed before information theory in the early 20th century. And the other side is a converse proof, which is basically to come up with an upper bound on the channel capacity. Now, within the scope of this talk, let's focus on achievability proofs. So achievability proofs rely on two ideas, two principal ideas. And that's the whole point of this talk. These two foundational ideas are basically, if there is a very complex engineering problem, you don't know the exact answer, but you can come up with a large family of functions among which you can prove existence of a function that achieves the objective that you are searching for. These are the two principles. Large family of functions instead of a specific function, and an existence proof that there is a function in that large family that achieves it. Now let me skim quickly through some example in wireless communication. And I'll do the same thing when discussing deep learning. So what that enabled us is basically it enabled us to tackle very complex problems in a hierarchical approach, even though we haven't settled on final answers for the simpler problems. Like, for example, let's take as a case study interference networks. Interference happens in wireless communications because of the broadcast and superposition properties of wireless communications, right? So if I transmit something, it just goes all over the place. It's not directed because it's not laser focused, right? So the frequency or wavelength at which wireless communication typically happens, at least before the higher frequencies like millimeter wave, enjoys this broadcast property. At the same time, it enjoys this superposition property, so interference can happen, right? So even for the simplest case of a two-user interference channel, 2x2 channel, we don't know the exact capacity, right? Then how come we can expect to make progress towards modern wireless networks where we have very large networks, like in a whole city, for example, and we want to analyze very complex things that because of technology advancement didn't even exist in 1948, like transmitter cooperation to transmit to a single receiver or to distribute the same message to base stations over a backhaul infrastructure. Right? So the foundation of information theory, or that mathematical theory of communication, enabled us to make progress towards the more complex problems, even though we haven't settled the simpler ones first. Right? So as an example, this cooperation example, we don't know, like we have a lot of research questions to answer regarding when is cooperation useful, how useful it can be, and what's the right resources or what's the right cooperation order so that we can start to observe practical gains, right? So this problem is very difficult. The exact capacity characterization is not known even for the simplest interference channels, but instead we have other metrics that are more rough and allow us to make progress towards more practical problems that we have nowadays. Like, for example, very large networks. We can answer questions about the potential of cooperation if we do clustering versus if we do something that's spiral, that's not necessarily clustering, but a more distributed assignment of messages or words over transmitters, right? So in this figure, for example, we denote by W a word or a message, and the word is going to the receiver that has the same index, so W1 goes to receiver 1 and so on. And you don't necessarily have a cluster, but you have this spiral assignment where you give W1 to transmitter 1 and transmitter 2, W2 to transmitter 2 and transmitter 3, and so on. So we could answer, because of the hierarchical approach, very complex problems about distribution of messages over base stations in a very large network and have useful conclusions. Right? Now, these conclusions and their proofs are outside of the scope of this talk, but I can refer you to papers if you're interested that settle these problems. Now, let's switch gears and go to the other side of this talk, which is deep neural networks. What are deep neural networks? They are basically an extension of neural networks where we don't have a good grasp on the final solution that they come up with regarding very complex tasks that we thought are infeasible to machine learning before, especially in image processing and language understanding tasks. So these networks basically contain a very large family of functions defined by all the possible weight assignments that you could have between the different neurons. But we do not predefine these weights. Instead, we define a mechanism to reach the right weights, the right set of weights for every task. So given a data set, we have a mechanism which is gradient descent or some variant of gradient descent, so that we can take feedback from the data set or from the error signal coming from applying the labels of the training set, so that we can reach a useful assignment of the neural network weights. Right? So here also, similar to information theory, we don't explicitly design a function for or reach a concrete engineering solution. Instead, we define a large family of functions, and we prove existence that among this large family of functions, there exists a function that solves the problem exactly. And this proof of existence comes through the data set that we have, right? And this is enabled both by the advancement that we have in hardware technology as well as the large data set, right? Something like deep learning could not be possible to achieve at the start of computing, right? We had to wait until we collected large data sets. So it's a natural evolution of the computing revolution in industry that started in the 1970s. Now this deep learning paradigm is becoming so successful that some people are predicting that it will become a computational framework. So even for hardware, at the hardware level, computation will happen through this machine learning approach. It's usually suitable for problems with inaccurate mathematical models and large data sets. Now, I argue in this talk that it's actually very suitable for next generation wireless communication networks because of the three reasons mentioned in the slide. It's out of scope of the talk to go into the details, but in summary, wireless communication is undergoing a major transformation where instead of having concrete models for the environments like in point-to-point communication channels or in small networks, next generation networks, it will be very difficult to have a concrete model. At the same time, because of the nature of wireless communication, right, or the speed of electromagnetic waves, that we can collect large data sets very easily. Like in a few seconds, maybe you can have hundreds of thousands of samples if you are trying to achieve a task at the physical layer scale, right? And not surprisingly, the last reason is related to the fact that the mathematical operations typically happening in neural network architectures are very similar to the popular mathematical operations happening in encoding and decoding in wireless communications, like convolutions or temporal correlations, right? So basically, the main proposal of the talk is that if we understand the lesson deeply from how information theory evolved and allowed us to make progress into scientific research and engineering solutions, then we can apply the same principles and come up with a hierarchical approach to applying deep learning in general into any new application, and specifically for wireless communications. So we can start, for the wireless communication case, from simple tasks like source identification to behavior understanding of single transmitter receivers, to context understanding and analyzing network behaviors. And relating that last step, where analyzing network behavior, there is an interesting case study. I invite you to read more about it. It was called the DARPA Spectrum Collaboration Challenge. DARPA is a defense agency in the US, and they have this nice tradition of doing research initiatives through challenges. A similar challenge in the 70s resulted in the internet, and another one in the early 2000s resulted in major progress in self-driving cars and deep learning. Right, so this one was about wireless communication, but a new vision for wireless communication where you have heterogeneously and independently designed networks coexisting in the same space or the same spectrum, and they only share a common language, and then it's up to them, or it's up to their AI, to figure out how to coexist intelligently in the same spectrum, right? And I was lucky to lead the Purdue and Texas A&M team in that challenge. So in summary, it was very interesting to apply some of the principles. In particular, it was interesting to collect a data set and start with some simple tasks like frame error prediction, and through these simple tasks, understand the insights that could generalize beyond that task to understanding deeper insights into what will happen when we start applying deep learning seriously into wireless communications. So there are a lot of concerns. I'm not saying that this problem is mature in any sense. It's still at the start, but this is really an invitation to start thinking about its aspects. We are only at the beginning of applying deep learning into a lot of very important engineering applications, especially wireless communication. Maybe one objective of this talk is to learn from the story of information theory, the successful story of information theory, into learning design principles, into how to apply deep learning into these new fields. And in particular, to learn the lesson of finding a large family of functions instead of an explicit engineering of a specific function, and augmented by finding a mechanism which was probabilistic existence in the case of information theory, and in the case of deep learning, it's something like gradient descent or some other optimization algorithm, a mechanism to find the right function among the large family of functions and to have a proof of existence. Thank you. It was a pleasure to give this talk.